Hey everyone, in this video we are going to talk about logarithms. Logarithms are the inverses of the exponential functions that we've been talking about in the previous video. So let's go ahead and take a look at how these work. All right, so I want to start by considering something that has nothing to do with logarithms, but it kind of gets us thinking about how they might work. All right, and so this thing is the following equation, x cubed equals 7. Okay? So how do we solve this? Well, I know exactly what to do. I'll just take the cubed root of both sides to find x. So if x cubed equals 7, we know that x equals the cubed root of 7. Now, we're fine with this. We know that the cubed root of 7 is a number. It's the number that when cubed gives 7. Let me write that down. It's the number that when cubed gives 7. And we could probably even surmise roughly what value that might be. And I know that 2 cubed gives 8, so it's a number a little bit less than 2, right? 1 cubed gives 1, so it's a number between 1 and 2, probably closer to 2, right? So we have an idea of where this number is on the number line, and we could use a calculator to get its decimal value to approximate it that way. Okay, well, what if I gave you the equation 3 to the x equals 7. How are we going to solve this? Well, this is where logarithms come into play. Okay, and the answer is, I'm going to go ahead and tell you the answer. It's x equals log base 3 of 7. And so what does that represent? It represents the number it's the exponent on 3 that gives 7. That's what x is, right? X is an exponent on 3, and it produces 7. Okay, the exponent on 3 that gives 7. So this might look really mysterious to you right now, but that's because you're just not used to it, right? Cube root of 7 is very mysterious to people. What does this symbol mean? Where does that come from? If you've never seen this symbol before, this is going to blow you away. It's going to look like, whoa, what the heck is that thing doing? What is that about? But when you get used to it, you come to terms with the fact that it means this. And then we can get an idea of what number it represents and where it is on the number line. Well, we're doing exactly the same thing. We're using some new symbol. Instead of this funny shape here, we're using this word, log, with a little subscript here. And notice how, just like we wrote the 3 over here, we're writing the 3 down here. So it's really completely analogous to this. And so just by getting used to these, you can come to terms with what these mean. But if you just think about it this way, the logarithm, log, gives you the exponent on 3. It's the exponent on 3 that gives 7. And that's what x is here. Okay. So how do we do this? How do we write this in general? Well, if I tell you that y equals b to the x, right? Then if I wanted to solve this for x, right, I would write x equals log base b of y, right? X is the exponent on b that gives y. X is the exponent on b that gives y. All right, so that's how we're going to interpret this. Whenever we see this expression, we're going to be thinking about it that way. Okay, so let's look at some examples. Okay, examples. We'll compute the following logarithms. See if maybe you can think of what these might be as I write them down. Okay. So here we go. Log base 2 of 8. What is this? It's the exponent on, what's the b here? It's 2, that gives What's this number here? 8. It's the exponent on 2 that gives 8. In other words, 2 to the what equals 8. Think about it a little bit, you realize that's the number 3. So that's what log base 2 of 8 means. It's the number that I would have to exponentiate 2 to get 8. Okay, what about log base 4 of 16? Well, it is the exponent on 4 that gives 16. So 4 to the what equals 16? Well, the answer is 2. What about log base 10 of 10,000? Well, that's the exponent on 10 that gives 10,000. 10 to the what equals 10,000. Well, I know that the exponent gives me the number of zeros here, so this must be 10 to the 4th. So logarithms give you exponents. When you're asked to find the logarithm, think exponent. I'm finding the exponent. Let's do some more here. Let's take a look at log base 10 of 0.1. Let's look at the log base 2 of 1/4. Okay. Well, log base 10 of 0.1. So what's the exponent on 10 that's going to give me 0.1? Well, what's 0.1? That's 1/10. What sends 10 to the denominator? A negative exponent. And it didn't change, so it must be a -1. 10 to the -1 is 0.1. What about log base 2 of 1/4? What's the exponent on 2 that would give me 1/4? Well, I know that 2 squared gives me 4, but I need it to end up in the denominator, so it must be a -2, right? Positive 2 would give me 4, -2 would give me 1/4. That's what negatives do. They send it to the denominator. Okay, so this is how logarithms work. Takes a little bit of getting used to, but this is how we compute them. Always remember that the logarithm is an exponent. You're trying to find the exponent. All right, next up, let's talk about logarithmic functions. Okay. A logarithmic function is just going to be a function of the form log base b of x. Okay, well, remember that when we dealt with exponential functions, this base here, that's our base, was not allowed to be negative or 0, and it was not allowed to equal 1. So b is positive and b is not equal to 1. So keep that in mind. We're not allowed to have b non-negative, and it can't be equal to 1. Okay. So, sorry, we're not allowed to have b non-positive, I should have said. So let's take a look at what these look like. Okay, and I think I have that hiding behind our, oh no, where did it go? That's weird. I had that set up and ready to go. I don't know why that's not. Here we are. Okay. Okay, let's take a look at what these graphs look like if we were to graph that function. Okay. Let's see here. So here I've got it set up. F of x equals log base b of x. Let's look at a b like b equals 2 here. There we go. If I increase the base, and I see the function kind of flattens out, right? It grows less and less. If I decrease the b towards 1, remember b is not allowed to equal 1, so you see it actually goes away when I get there. If I go less than 1, look at this. It's the same thing but upside down, right? It kind of flips upside down. Now notice that there are some things that aren't changing here, all right? For one thing, what's the domain of all these functions? What values of x give me an output? Well, any positive value of x. Notice that there's no graph to the left of 0. Graph doesn't live over here. It only lives over here. Why is that? Well, remember that log base b of x is the exponent on b that gives x. Now, b is a positive number, and so if I put any exponent on it, be it positive or negative, I can only get a positive number as an answer. So that means x can only be positive. All right? So that's why you don't see a graph over in the negative region over here. What else is going on with this graph? Well, all these graphs, no matter what b is, they all have an x-intercept right here at 1, right? The point 1, 0 right there is the x-intercept, and that's true for all of these. Why is that? Well, what that's saying is that log base b of 1 is always equal to 0. Well, that should make sense because 0 is the, if you use 0 as an exponent, you always get 1. Right? So anything raised to the 0 power is 1, except 0, which is undefined. But we're not worrying about 0, right? So b can't be 0. So that's why the x-intercept is always the point 1, 0. What else are we seeing here? We're seeing that all of these graphs have a vertical asymptote. Notice that they approach the y-axis. They get closer and closer to the y-axis. They never get there, though. If I zoom in, I'll see it never actually gets to the y-axis. But that makes the y-axis a vertical asymptote. The y-axis is the line x equals 0. Okay? So let's just make note of these observations. All right. So our observations were the domain is the set of all x greater than 0, so the interval 0 to infinity. We had the x-intercept was always the point 1, 0, and we had a vertical asymptote which was the line x equals 0, that vertical line. Okay, let's just graph one of these by hand. I want to show you that this is possible if we choose a reasonable base. All right. So let's go ahead and graph y equals log base, let's make that a 2, log base 2 of x. All right. So all right, well, let's mark off some values here. 1, 2, 3, 4. And remember that 1, 0 is always an asymptote. Sorry, an intercept, right? So there's our intercept right there. If I take 2 for x, what's log base 2 of 2? Well, that's the exponent on 2 that gives 2. Well, that's 1. So if I mark off some values here, the exponent on 2 that gives 2 is 1, so I have that value. 3, I don't think I can get a nice value for 3, but if I go to 4, what's log base 2 of 4? What's the exponent on 2 that gives 4? Well, it's 2. 2 squared is 4. So I see we have a value there. Right? And I know that the line x equals 0, the y-axis, is a vertical asymptote. So I can see that the graph looks something like this. So we can get an idea of what the graph looks like without even using any fancy graphing software, just by understanding how to compute some basic logarithms. Okay? Okay, so what I want to talk about next is some special logarithms. All right? Sometimes we use very special bases. It's very commonly done that we use base 10. Right? That b becomes 10. And when we use base 10, we just call that log. Almost always, if someone writes log without a base, what they mean is base 10. It's just like when someone writes this symbol, what they mean is the square root. Right? They don't write the 2, but that's what they mean. It's just so commonly used that we just, get rid of the number so we can write it down quicker. Same thing's happening here. So commonly used log base 10 that we just don't bother writing the 10 anymore. Okay, so let's look at some examples here. All right, let's look at log of 100. Look at log of 1,000. Look at log of 10,000. All right, and then we'll look at some other logs. How about log of 0.1, log of 0.01, log of 0.001. Let's find out what these are. Well, remember, the implied base here is a 10, right? So I'm thinking, what's the exponent on 10 that gives 100? In other words, 10 to the what equals 100? Well, I know that 10 squared gives 100, so this guy is equal to 2. What about log of 1,000? What's the exponent on 10 that gives 1,000? I'm going to let you think about that one a little bit. Why don't you pause the video, see if you can figure these two out. Okay, 3, 2, 1. All right. So you should have gotten 3 here. 10 cubed gives you 1,000. And you should have gotten 4 here. 10 to the 4th equals 10,000. Now what about these guys? Well, we actually did this one earlier, right? I wrote the 10 down here, and we said that we're looking for 10 to the what equals 0.1. Well, remember, we realized that was 1 over 10, and so that had to be -1. So what about these two? Go ahead, pause the video, see if you can figure these out. Okay, pause, 3, 2, 1. Welcome back. Let's see. 10 to the what equals 0.01. Well, 0.01 is 1 over 100. So I know that 10 squared gives me 100. If I want 1 over 100, it must be 10 to the -2. There we have it. What about this one? Well, we're asking 10 to the what equals 0.001. Well, that's 1,000th. 10 to the what gives me 1,000. That's 10 to the 3. But I want 1 over 1,000, so that must be -3. And this log is used in many applications. If you've ever heard about the Richter scale to measure earthquakes, the magnitude of earthquakes, those are logarithms. A magnitude 7 earthquake is 10 times more powerful than a magnitude 6 earthquake. And a magnitude 6 earthquake is 10 times more powerful than a magnitude 5 earthquake. The Richter magnitudes are actually logarithms, log base 10. It's also used when we measure pH, and that is how acidic something is. The lower the pH, the more acidic it is. So if you look at a pH of 6 compared to a pH of 7, right? The 7 is 10 times, actually I should say, since acidic is actually going down, basic is the opposite of acidic, so basic's going up. So a pH of 7 is 10 times more basic than a pH of 6. And a pH of 6 is 10 times more basic than a pH of 5. And the pH is the H stands for hydrogen. It's the concentration of hydrogen ions in the solution, and that's what makes something acidic or basic. All right. So finally, I want to talk about one other special logarithm, and that is log base e, and that's called the natural logarithm. The natural logarithm, they call it natural because it kind of pops up in a very natural way, kind of like pi pops up when you measure the area of a circle, or the circumference of a circle. It's just there. It just happens. And so it's a very natural number. It just happens. You don't need to make it up. Like degrees, you make it up. You just divide the circle into, we decided, 360 parts. There was nothing natural about it. But pi is very natural, right? Same thing happens. The number e in mathematics just comes up very naturally. And so when we take a log base e, that's called the natural logarithm. So remember, this number e is the number 2.71828 ... It goes on forever without repeating. It's an irrational number like pi. It's a very commonly seen number in mathematics. It comes up in a lot of natural scenarios. We saw it when we talked about continuously compounded interest. It came up there, for instance. And so because of that, we like to give it a special name. So we don't have to write log base e all the time. We just write ln. Right? So ln means log base e. So what would ln of these values be? See if you can compute some of these while I'm writing them down. Let's make that more interesting. Let's put a 13 there. Let's do another one, e to the pi. All right. Oh, let me put one more in here. Okay. Say, we can fit it on the screen. Why not? All right. What's log base e? Well, sorry, log of e, the natural logarithm of e. Well, remember, this is log base e, right? So this is asking e to the what equals e? Well, anything raised to the 1 power is itself, so that must be 1. Okay, what about natural log of e squared? E to the what equals e squared? Well, it's kind of obvious, right? I mean, what does this number have to be so that this looks like this? Well, it needs to be a 2, right? E to the what equals e cubed? What does this have to be? A 3. That'll make these the same. See what it's doing? The log is just pulling down the exponent, right? Log of e to the negative 1. E to the what equals e to the negative 1? No, it's negative 1. What about this one? Negative 2. What about this one? Negative 13. What about this one? E to the what equals e to the pi? Pi. How about this one? E to the what equals 1? E to the what number equals 1? Well, take a positive number. If you raise any positive number to 0, you get 1. That's always true, no matter, even if this wasn't an e. So this is always going to be a 0. Even if this wasn't log base e, that would have been 0. Let's do another one. Let's do log of 1 over e to the 5th. E to the what equals 1 over e to the 5th? Pause the video, see if you can figure this one out. Think about properties of exponents. 3, 2, 1. Okay, welcome back. Well, I'm going to write this a different way, just like we did with some of our previous examples. Remember when I had 0.1, I wrote it as 1/10. Well, you can do similar tricks here. You can write this with a negative exponent here, e to the negative 5. And now I see the question mark needs to be negative 5. Natural logarithms. So this is how logs work. So we talked about logs in general, and we have these two special logs, log base 10 and the natural logarithm. All right, so I think that's it for this video. It definitely is. So catch you next time.